I will talk about hydrodynamics and collective flow in heavy ion collision. So it will be at a very basic level. This I must declare in before I begin, and it may be boring for some of you, but please bear with me. Okay. So let me start with this picture you have seen maybe hundreds of times already. It's a good one. So this was made by Chun Shen, and it shows the stages of heavy ion collision. Is my pointer visible, Partha?
Yes.
Okay. Okay.
Yes,
Thank you.
visible. Pointer
Okay. Nice. So this shows a collision of two Lorentz contracted nuclei, which goes through a pre-equilibrium dynamics, which we know a little about this phase. But once a near equilibrium has been reached, then the system essentially kind of thermalizes and undergoes a hydrodynamic expansion. We also consider viscosities for reasons I will come to later during the talk. And this is the QGP phase that we know of. Now it is more or less well established that QGP has been achieved in, seen in RIC and LHC collisions, high energy RIC and LHC heavy ion collisions at least. And yeah, and then basically the system thermalizes and squeezes out essentially, and you see hadrons in the final state. Okay. And this is what kind of anyone giving a talk on hydrodynamics will show you. So this is kind of slide which tells you what hydro does to the initial state anisotropy. It takes it to the final state momentum anisotropy, from position special information to final state momentum anisotropy. Okay. And you will hear words like pressure gradients being converted to anisotropic flow, and conservation laws, which is essentially these two tensor equations, the divergence of energy momentum tensor equal to 0 and four current vector equal to 0. Yeah. So and then okay, so the idea is that I will, in the next few slides, I will go through step by step of what hydrodynamics really means, why these equations actually imply conservation equations. What do we really understand from this energy T mu nu, these tensors and this vector 4 vector? What do they really mean physically? And then we also learned that viscosity is required to agree with the data for the flow, for example. And this is one of the very first plots done by Paul Romatzke, and where he shows that if you include viscosity, then the elliptic flow is suppressed, and more or less this is what is required in the to match the experimental data. Okay, and on the left hand side we see cartoons for collision overlap geometry, where one can calculate eccentricity, and this develops further into flow, the elliptic flow, which we call the coefficient V2, and it essentially captures the elliptic anisotropy in the momentum space. Okay. So what? So we'll also in this talk I will also discuss what viscosity imply, what does viscosity mean, and how it affects the observables. So the first part of the talk, hydrodynamics. So kind of in a very simple form. So I will start with something which I will assume everyone is familiar with, the phase space distribution function for a relativistic particle. Okay, so this is the energy momentum relation for the relativistic particle. P0 is the zeroth component of the 4 momentum vector, which is the energy of the particle, and f of xp is the distribution function. It is defined such that this quantity f of xp delta 3x delta 3p, it gives the average number of particles in a volume element delta 3x. Okay, and that is at a point p in the range p plus delta p. Okay, so in the phase space, essentially f of xp represents density in the phase space. Okay, of course it has some assumptions on which it works. So number of particles in the volume element is large, the special volume element is R, so you can make a statistical average. But this special volume element that we are considering is small compared to the total volume of the system under consideration. Okay, so there are statistical assumptions we make. So within this picture, I can define number density, particle number density, which is such that if I take the number density and multiply the volume element, we get the number of particles in this small delta 3x volume, which is located at x. Similarly, one can define particle flow, which is the particle current along x, y, or z direction. And together they constitute the particle force flow. So how do we define these quantities? The density is, so in terms of the phase space distribution function, remember f of xp is density in the phase space. So if I integrate over the phase space volume, over the momentum volume, then what I get is density in the spatial volume, because I just integrated over the momentum volume. Okay. And similarly, if I weigh the distribution function with velocity, so this gives you particle velocity. So v is the particle velocity. If I weigh it with the distribution function integrated over the momentum, I get the current. So whenever I want to calculate some quantities, I will weigh it with the relevant factor. For example, here to get the current, I weigh it with the particle velocity. To get the number, I weigh it with 1 essentially. This is 1 count per particle. Okay. So then I get the density and current. Remember, v is the relativistic velocity. V is momentum by energy. That is the velocity. Okay. So particle force flow can be, together combined. Together, these two quantities can be combined to write it like this. And automatically you see that a d3p by p0 appears, which is a Lorentz invariant momentum integration measure. Okay. So owing to this fact, we can see immediately that n mu is a particle 4 current. It's a 4 vector, because p mu is a 4 vector, d3p by p0 is a scalar, and f is a scalar. We will see the consequence of demanding f to be scalar later. Similarly, we can construct the energy momentum tensor. So we start with the energy density. T00 I define to be the energy density. So to calculate the energy density, I weigh the distribution function with the energy per particle and integrate over the momentum. So that will be the density of energy in spatial volume. Okay. So that this can again be written like this in this form. Similarly, we can define energy flow, which is weighed with energy of particle times its velocity. So flow of energy. Okay. And integrated with the distribution function, that gives me energy flow. Momentum density is defined as weighing with the momentum and integrating over the volume, momentum volume. Okay. So this is momentum volume. One can momentum density. One can also define momentum flow. So this is the ith component of momentum flows along jth direction. Okay, so this is ith component of momentum, and weighed with the velocity of the particle along jth direction, and that gives me momentum flow. So all this I can combine together in again a covariant form, which I call energy momentum tensor. So this is how I understand the components of energy momentum tensor. Okay, and particle force current. So what does conservation? Yes.
Excuse me.
Yes.
There is a menu bar coming on the top of the screen.
Okay.
Can you put it down somewhere or hide it up? Yeah, this is okay. Thank you.
Okay, thank you. Also, I encourage to please ask students or anybody, please ask questions in between. I mean, it should not be a very formal talk. It's a lecture, so please feel free to ask. Okay. So once I have defined my conserved current, so particle current and energy momentum tensor, let's see what the conservation really implies. So we just saw that the particle number density is the 0th component of n mu, particle force current. Okay. And when I write normal font T, normal font X, that has time and vector X. Okay. So this is 4 vector X, So it's x mu essentially. Okay. So particle current, or the total particle number. The total particle number would be now the particle density integrated over the volume of the firewall, or whatever volume of the system I have. Okay. So this is the total particle number in the system. Okay. So conservation of particle number essentially is just this equation, that the particle number, total particle number doesn't change. Okay. The ddt of n is 0. Now what I can do is, that is the left hand side being 0. So I can take the right hand side of this total number expression and rewrite it. So this is what n0 being a function of time and x vector x. Okay. This is a partial derivative, to which I can add a total divergence term. So this is a total divergence. This derivative of ni with respect to xi. Remember, the integral is over x. So I can always add a surface term, because surface term doesn't contribute to the, it has to vanish. The physical quantities have to vanish at surface, because beyond the surface there is no system. Okay. So I can add this total divergence term to the surface, which is the surface term, to del n by del t. Okay. And these two can be combined in this form, in a covariant form. In the covariant form. Okay. So the integral volume being arbitrary, so since we're integrating over an arbitrary volume, so this has to be conserved. So del mu n mu has to be 0. Okay, where del mu is defined as this derivative with respect to x mu. So this is what really conservation of particle 4 current means. So the total number being conserved gives you a conservation equation for the particle 4 current, which is the hydrodynamic quantity. Similarly, I can start with energy density, which is the T00 component, and momentum density, which is the T0i. I can, since T0i and Ti0 are symmetric, I mean, since the T mu nu is symmetric, I can, these are the same thing. Okay. So this is energy density and momentum density. So these are all densities. Okay. So I can define a total for momentum of the fluid under consideration, which is which is the energy density and momentum density integrated over the whole volume. Okay, so this is just the whole momentum of the whole fluid, the energy and momentum of the whole fluid. So what now I demand is conservation of total energy momentum of the fluid, which is that it does not change with respect to time. So dt of this P nu has to be 0. Again, we play the same game. So we look at the right hand side of the conservation equation, and we see that we can again add this total divergence term, the surface term, which gives us the conservation of energy momentum tensor. Okay. So the idea is that we have to first actually recognize what these components mean to be able to understand what the conservation equations mean. Okay. So this is so this is just, that's it. I mean, this is what hydrodynamic equation tells you, that the conservation of total particle and total energy and momentum these are the conserved quantities, and therefore we get equations in terms of for these this tensor like equations that we saw. Okay. So moving ahead, what we will do next is we'll try to construct these tensors in terms of fluid variables. Okay. So let's look at system in absence of dissipation. And this implies, so if there is no dissipation, there is no entropy production during the evolution of the system, and therefore the system is in equilibrium. Okay, so we can express these quantities which we already derived in terms of distribution function by putting f equal to f equilibrium. Okay, and this is the equilibrium distribution function, the well-known form of distribution function, which is so if there is this r parameter which I can tune, r equal to 0 will give me Maxwell-Boltzmann, the classical distribution function. R equal to 1 will give me the Fermi-Dirac, and r equal to -1 will give me the Bose-Einstein distribution function. Okay. So, but there is a problem. The problem is that in this form, E is the 0th component of particle 4 momentum in this form. So I cannot, this is not a Lorentz scalar, but what I demanded was that for T mu nu to be, or N mu to be a Lorentz 4 vector or 4 tensor, essentially, I have to have F equilibrium as a Lorentz scalar. So this can be achieved by expressing it in this form, which is also known as the Yatner form, where beta is 1 by t and alpha is mu by t, but I introduce a vector u mu, okay, which is dotted with p, such that when u mu is 1 comma 0, we recover u dot p becomes just p0, and we recover the well-known form. Okay, so u mu has to be 1 comma 0 in one frame, such that we recover the known form. Okay, therefore u mu has to be 1 no matter in which frame, because this dotted quantity is a Lorentz scalar, so this has to be 1. Okay, because we need one frame in which we recover the physically understood distribution function, so we have to have u mu equal to 1. All right.
Yeah, I have a question. Can you
Yes.
ask?
Yes, please.
Yeah, so this distribution function R is a variable.
R is a variable, yes.
The position of it's only position coordinates, right?
R is not position. R is this quantity 0, 1, minus 1.
Okay,
I'm sorry.
Constant. So where X is absorbed, that is my.
No. Till okay, local. I just said local. I agree. So X is there in beta, U, and alpha. So I will finally make this
Beta
quantity.
Okay.
Okay, beta, U, and alpha. I will make them position dependent. Okay.
So that way I got to. Thank you.
Okay. Thank you. So this is what I'm going to do, and then okay. So before that, in this distribution function, let's count.
Excuse me. Again, sorry to interrupt.
Yes, please.
Yes. So the quantity that you wrote here, you knew, and there is 1 comma 0. What does this 0 vector means? Essentially, I mean, how do you connect this 0 vector with something?
Okay.
I just trying to understand.
So this is like, u dot p is something which I define such that u mu is like a velocity vector. So this 1 comma 0 means that so when the velocity vector, so the three velocity is 0, which implies the fact that I am locally at rest with the fluid.
Okay.
Okay. So u mu 1 comma 0 means that there is no 3 velocity, so I am at rest with the fluid, and then in that case we see that the distribution function is the distribution of the this well-known distribution function that we already know. So the point being that these distributions, the Maxwell-Boltzmann, Fermi-Dirac, Bose-Einstein, are defined, for example, for a gas for a box of gas. Yeah, in a box you have a gas, and that box is at rest with the lab. Okay, so this distribution function holds. Okay.
Yeah, so the distribution is for static systems, right?
For the static system. But what I'm trying to do is, I cannot have this in the static case because E is the 0th component of particle momentum for momentum. So this then becomes manifestly Lorentz invariant quantity. I want to make it Lorentz invariant. So I define a vector, a velocity vector, 4 vector, with which I dot the momentum, particle momentum, such that in one frame at least I recover the known results. That is this frame. Okay. And
yes, I got it.
Okay, and the fact that this in one frame u mu is 1, 0, so u mu has to be 1 in one frame, and then that remains 1 in all frames because it's a Lorentz invariant scalar. Okay, so this is the fundamental property of the u mu, that it is normalized to 1. Okay, then in this distribution function, let's count the.
Interrupt you, Amaresh. So
Yes,
then u mu at any frame, since it is u mu equal to 1, a Lorentz scalar, so any frame, the construct of u mu would be such that it become a Lorentz scalar. So that u mu will give us 1.
Exactly. U mu will be 1 in any frame. Yeah. Because because in one frame, if we get it to be 1, then the norm of this
right, norm remains unchanged when you transform.
Exactly. Yeah. Right. Okay. So then in this distribution function, I list the tensor degrees of freedom. So there are 2 scalars, temperature and chemical potential. Alpha is mu by T. So temperature and chemical potential are the 2 scalars. There is only one vector, u mu. P is integrated in hydrodynamic currents. So hydrodynamic currents are defined by integral over P. Okay. So P is integrated. So there is only one vector, u mu. And there is one tensor, g mu nu, because u dot P, to define u dot P, you require this metric tensor g mu nu. Okay. And nothing else. R is just a parameter. So R is not a variable for us. Okay. So this is what completely defines my equilibrium. These 2 scalars, one vector and one tensor. So the hydrodynamic currents can be expressed most generally in this form, the n mu and the t mu nu. Okay, most generally you can express it in this form. Remember, you cannot write any other term because u mu is 1, and therefore no new terms can be generated. So this is the most general form you can write, where C1, C2, and C3, which are the coefficient of these vector and tensor terms, these are Lorentz scalars. C1 for them to be vectors and tensors. So that, yeah, so these are Lorentz scalars, C1, C2, C3, but we only have two scalars, T and mu, to define equilibrium. C1, C2, C3 have to be related via some equation, which we call the equation of state, because there are only two independent quantities, okay, T and mu. So out of these three, there will be only two independent quantities, and they are connected by equation of state. Okay. So this is how we recognize that there must be an equation of state at play here. Okay. And then next is how to determine the form of C1, C2, C3. So for that, we consider the physics of hydrostatics. Okay. So we go to a frame where the fluid is locally at rest. Okay, we call that local rest frame. So from hydrostatics, what we know is that if I go to a frame then where fluid is at rest, I will only see particle densities. There won't be any flow because nothing is moving with respect to me. So I only see particle density and 0 for the flow. For the energy momentum tensor, I will only see energy density and pressure. This is, and pressure, that too equal, Pascal's law, pressure equal in all directions. Okay. So that is pressure, and there is no flow, no momentum flow, no energy flow, nothing. So these components are all 0. Okay. So this is what I know from hydrostatics. Now this form that I wrote down for n mu and t mu nu, I can go to the local rest frame, u mu equal to 1, 0, 0, 0. This is what I define as the rest frame. Okay. And express these quantities, t mu nu and n mu. So they take this form. When u mu is 1, 0, 0, 0, of course I have used g mu nu equal to 1 minus 1, so mostly negative sign. I should have mentioned that, but yeah, mostly negative sign for the metric tensor. Okay. Then I get this form for n mu and t mu nu. Okay. And then comparing these two, the hydrostatic picture with the form that we already obtained from the tensor arguments. Okay. We get these values of C1, C2, and C3. C1 is just it's very easy to see. That's the number density. C2 is energy density, and C3 is energy density plus pressure, and C3 is minus P, negative for pressure. So this is the form of the conserved currents, N mu and T mu nu. Okay. So to derive this form, all we needed was the equilibrium to be defined. Okay. And we can see that these coefficients C1, C2, and C3 are indeed thermodynamic quantities, and they have to have some equation of state for them. Okay. So let me now connect these two pictures, this whatever we derived, to non-relativistic case. So consider incompressible. So this result I show is for incompressible non-relativistic fluid. There is a trivia: absolute incompressibility is not allowed by relativity. So this you might have already come across. But however, we'll just for the sake of comparison, we look at the non-relativistic continuity and Euler equation, and we also look at the conservation of energy momentum tensor. It leads to these two equations. Okay. So this derivative I have defined here, these two derivatives, d and nabla mu. Okay. So this is just a convenient way to remind ourselves, I mean, at least to have an intuition that d is just, it behaves like this derivative, roughly time derivative and derivative along the fluid velocity. And nabla is roughly space-like derivative. It's a gradient. Okay. So what we see is that if I compare these two Euler equation, non-relativistic Euler equation, and this hydrodynamic equation, relativistic hydro equation, the counterpart of Euler equation, I see that there is a spatial gradient of pressure which leads to change in fluid velocity. Okay. So I will come to that. So we have to keep in mind that spatial gradient of pressure leads to change in fluid velocity. And there are certain differences with respect to non-relativistic case. So the inertia of the non-relativistic fluid is defined by rho, which is just the mass density. Okay. Whereas it is defined by for the inertia of the relativistic fluid, it's epsilon plus P, energy density plus pressure. Okay. So in the non-relativistic case, you will see that viscosity, specific viscosity is defined as eta over rho. Whereas in the relativistic case, we define as eta over S. This may be the reason. As you can see, the S takes this form. So that's why we really worry about eta over S. Okay. More trivia. The number conservation is redundant in non-relativistic case. So we have this continuity equation for mass in the non-relativistic case. Okay. And we don't worry about number conservation because whatever the conserved charge, particle number, it just flows with the mass. The mass and the charge sits on the particle, and that's it. So if you can consider one of them, the other is automatically guaranteed. In non-relativistic scenario, that's not the case. In non-relativistic cases, we worry about net number density, which is, or net charge, which is conserved, because there can be particle pair production, okay, or annihilation. So the energy or momentum conservation does not guarantee charge conservation. It has to be imposed separately because of this, and pair production is a purely relativistic feature. You don't see that in non-relativistic cases. Okay. All right. So this is the relativistic Euler equation. Gradient of pressure leads to change in fluid velocity. That's what we mean when we say that, initial, pressure gradient leads to an isotropic flow. So if I look at the pressure at the center of the fireball, which is P, then outside it must be 0. So it goes to 0 faster along X compared to along Y. So so the pressure drops to 0 more quickly along X as compared to along Y. Okay. So there is larger pressure gradient. So gradient of P is larger along X compared to Y, and therefore the fluid velocity, so basically the fluid gets more velocity along towards X direction as compared to Y, and that's what shows up in the particle momentum that we observe in the detector. So it's like, the fluid is pushing the medium outwards faster along X compared to that along Y, which essentially leads to more momentum of the particles in the X direction compared to the Y direction. Okay. And this is what we call V2. Okay. These are the definitions of eccentricity and elliptic flow. And hydro is the equation which takes me from, so I take this initial condition with spatial deformation, and it leads to final momentum anisotropy, okay, of the particle. So this is what hydro does. Okay. However, fluids are any medium is in general dissipative. That this is like it follows from uncertainty principle. So there has to be some dissipative features which has to be taken into account. So I will not go into details of how these terms are obtained. Suffice it to say that I have to correct the ideal energy momentum tensor and particle forecurrent by these red terms, which are dissipative quantities. Okay. And these dissipative quantities, so this capital pi we know as the bulk viscous pressure. This pi mu nu is the shear stress tensor, and n mu is the dissipative charge current. Okay. So, and they have to be derived in some way. So the equation for these have to be obtained in some way. Okay. And usually that is done by the appealing to the second law of thermodynamics. Okay, so we write the entropy forecurrent and we demand that this entropy forecurrent divergence. Yes.
The term corresponding to bulk viscosity is a scalar, and that corresponding to shear viscosity is a tensor.
Yes. So capital pi is so this is a scalar, a tensor, and a vector dissipation. There are 3 types of dissipation here in this picture. Okay. So this so capital pi is the bulk. So this is essentially a dissipation which resists the change of volume. So an overall expansion is inhibited by capital pi. Pi mu nu is shear stress tensor. It resists the change of shape. So if you try to deform the medium, this is the resistance given by the fluid. And n mu is the charge current. For example, if I put voltage across the medium, then how is the correct electricity, transmitted and so on.
This is a change of flow then.
change of flow, particle, yeah, if particle flow or charge flow if the field, if the field.
Depending on how you define your N. the
Exactly, yeah.
Density.
Right. Okay. So then the way we derive it is we simply define our entropy current and demand that the entropy for divergence is positive definite locally at each point. Okay. And one lands up with this equation. There is some steps in derivation. I will refer to some references as well.
Sorry,
Yes.
Amaresh.
Yes.
Earlier you said that for non-relativistic, when you were discussing Euler equation, for non-relativistic case, the mass density is now replaced by E plus P. And you said that this entropy density S is E plus P by T. And then you argued this is probably the reason when for our case, in relativistic case, while specifying the specific viscosity, we write eta by S instead of
Yes.
eta by rho.
Yes.
But then there you basically, here you use this E plus P by T for S. So
Right.
this is true only when your net number is 0, right? Because
Right.
here it's E plus P minus mu N.
Right. So that's why when I compared with the non-relativistic case, okay, so non-relativistic case, it does not have this, net conservation. So because there is no.
Yeah.
Okay. So then I simply looked at this quantity rho, which appears with this term, and what is that counterpart when I have an equivalent picture in the relativistic case without any conserved currents. That is what this is. So then what we say is that okay, then the specific viscosity must be divided by epsilon plus P, but not rho. Rho is anyway not a good relativistic degree of freedom. So one has to, of course, correct for, as you mentioned, if there is a net number conservation, okay, then entropic density has to be corrected for. And indeed, in the specific viscosities, S does have this. And when we talk about eta by S, in relativistic case, S does have this minus mu N. Okay, it was just so when I compared with non-relativistic case, it was just motivation of why we use this eta by S, just to get a picture. Okay. So then these dissipative quantities which we obtain, so now this is the expression that we obtain from second law of thermodynamics in covariant form, and we can see that it depends on a gradient, a hydrodynamic gradient, and a coefficient. So all of them has a hydrodynamic gradient and a coefficient. Okay. So this is what we will also expect, that for example, if there is this, for example, if I look at the current, so if there is a difference between chemical potentials at two ends, then only the particle will flow. Okay. Or heat current, for example, if there was heat current, then the temperature difference would lead to flow of energy. Okay, and so on. So this gradient is required, and these coefficients are material properties. How viscous it is, or how resistive it is given by this eta, zeta, and kappa, and it depends on how the particles of the medium interact among themselves. Okay, these are material properties of the medium. So dissipation has to have two components to it: a difference in at 2 points, a difference between hydrodynamic quantities, so a gradient of hydrodynamic fields, and the material property to support it. So these two combined together will lead to dissipation. So if eta is, for example, 0, then even if there is gradient, there is no dissipation. Okay, so this we have to keep in mind. Okay. Okay, so this is the picture that we have. So shear viscosity, for example, it resists the change of shape. Bulk viscosity is a resistance to the volume of the fluid, and then there is charge or heat conductivity, which, for example, depends on temperature or chemical potential difference between 2 points. Okay, and one can express this in terms of write in terms of gradients and try to get a feel of it. Okay. Now, this picture I come back to again. So we need to have dissipation in the system, at least in heavy ion collision. In the context of heavy ion collision, we need to have viscosities to suppress the value of V2 such that it has agreement with the data. Okay, so this is what viscosity does. So V2. So as we saw, V2 depends on epsilon2 in the picture with this initial eccentricity and final momentum anisotropy. This eccentricity, initial eccentricity, okay, it has two directions, so x and y. So it is initial, so it represents anisotropy in x and y direction. Okay, so the flow is, so this V2 essentially measures a preferential flow, more. So whether it's more towards x, it's more towards x than compared to y. Okay, so this is very sensitive to shear viscosity. Okay, and one requires a very small value of shear viscosity, small but finite. You need to have a small but finite
Sorry,
value.
Amaresh,
Yes,
you have used eta by s 0.03.
this
Is
this
it
is what
lower than this case is
0.08. Yeah, so this is what Romatsky used. This figure is not mine, but yeah, I mean, he just to test, he checked three values. So this is, so for example, this one is 0, eta by s is 0, the solid green one. Okay, so he checked with which is the ideal.
Just
Yes. Yeah. Okay. So so the idea is that, you know, viscosity, you know, suppresses the flow, and you have to suppress the flow. Ideally is not good enough. Okay. Of course, this is a very rough calculation. People have done more realistic, you know, calculations for this.
hello,
Yes.
But-
Yes.
hello. Yeah. So what I was saying that the case is bound. So it's not a very robust calculation, I think. So 1/4 pi one can take less value also eta by s can check.
There has been some cases of, you know, some classes of field theories do violate this cases bound, one has seen, but yeah, but for the time being, what we do know is that there has to be a lower bound. Okay, whether it's 0.08 or something else is debatable, but there has to be a lower bound to eta by s. That comes from more fundamental uncertainty arguments. Okay, nevertheless, the point is to get a good agreement or agreement with the data. We do need a finite but non-zero eta by s. Okay.
Amaresh, to George, Amaresh, the data shows some kind of saturation also, right? For
Right,
large
right.
it is becoming flat.
Right.
Which is also hydrodynamics, whether it's ideal or whether it is viscous with some amount of eta by s, is also unable to reproduce that saturation nature, right? It's still increasing.
Right. So, I mean, I must say that this is the first plot, the very first plots. Okay, so if you look at the calculations from recent calculations from music, and they get a very good agreement. Although at very high PT, I would not then be very certain about hydrodynamics working. So at for example 4 GeV is already a bit high, I would say, for star. Okay, so if I can get agreement up to 2.5 GeV or 3 GeV, but this is, of course, this is the first calculation of Romatsky. So there has been more you know, more sophisticated simulations, and they show good agreement with V2, V3 up to higher orders as well. Okay. All right. So just to compare with some viscosities, it turns out, so this is a very famous experiment, by the way, you can find it on Wikipedia. So it's like there's a tar drop falling every decade or so, and then they measure the shear viscosity of tar to be 10 to the power 11 times that of water. But QGP, shear viscosity, even larger than that of pitch. This, whatever this thing is. So the idea is it's not the shear viscosity itself, the magnitude of shear viscosity, but rather eta by s, which is small for QGP. That is less than 3/4 pi, and this is the quantity which is relevant for dynamics of the system, eta by s. Okay, and that, if you see, that is for QGP, it seemed to be, you know, so on the, for example, this red is for QGP, rather red is for QCD medium, I would say. So on the right hand side there is this QGP, and the left hand side is meson gas, and there is indeed, there looks to be some kind of, you know, approach to a minimum value of eta by s. And of course, this is less than other values, all other values of which is measured for other fluids. Okay. This IE is intermediate energy collision, so they also produce some values. But nevertheless, if you join them, these curves, that lines are just for to guide the eye. So it's not some fit or something. Okay. Okay, so this is all about hydrodynamics. So
Yeah, Partha, I think sorry, Amaresh, I think I missed. What is the importance of eta by S? How it appears?
okay,
If you could explain it.
okay, so it's intuitively what I would say is eta by s would be something. So just for example, if you have a medium and viscosity, what it does is it leads to dissipation of momentum, for example. Okay. So
Yeah.
if there is momentum, then this momentum gets dissipated. Let's say shear viscosity, the momentum gets dissipated and the temperature of the medium increases. It becomes a heat. It goes to heating the medium. Okay. But that is not a good quantity because you can have a system where the temperature is very high. Okay, like QGP. Okay, so then actually the dissipation will be a little amount of dissipation would be a huge amount. I mean, if you just compare a dimensional quantity with that of water. Water is at a temperature which is much lower than QGP. Okay, and really low. So then it's not a good quantity to compare. It's the relative loss of energy, which is what is a good quantity to compare. Okay, that's why eta by s plays a that is a
Maybe
dimension.
I was looking for some explanation from ADS-CFP side that they say that one corresponding from eta by S to from ADS-CFP side, something like that. Yeah.
Eta by s is okay. So it is okay. Well, that they just give a lower bound, right? Eta by s 1/4.
Yeah.
Okay. You wanted some other answer? I'm not sure.
No, but fine. I understood. Yeah, well, one more thing. I think
Yes.
like we are moving in the next topic, so I think it's
Yes, sure.
So this one like you have discussed dissipative part. So first order and second order. So I think you have not mentioned first and
No,
second
I will
order.
not mention that because that would require me to go into causality, stability aspects, and I did not. I wanted
So
to keep it at
I don't know why first order give causality violation, right? Because second order always is small correction kind of stuff.
Okay, so the first order gives causality violation. I can at least motivate from this equation. This is the first.
Yeah.
This is the first order hydrodynamic in the sense that there is only only one derivative order. Okay, this expression. Okay, so what it says is that derivative is like it acts. Derivative is defined as a distance as a difference between 2 points which are spatially separated. There is a space-like separation of 2 points, and you are looking at a current kind of thing between these 2 points. Okay, and then the left-hand side is essentially dissipative force. Okay, so what this equation tells me is that as soon as there is a gradient produced in the system, that immediately leads to a generation of a force. So this is the immediate effect. This is not allowed by relativity. Nothing can be instantaneous. Okay. So
therefore
that's what leads to violation of causality. So then you have to correct it by putting a relaxation kind of term, which says that indeed it relaxes to this, but over a time scale, and that time scale leads to restoring of causality. That is the second order theories and so on.
Thank you.
Okay. Okay, so collectivity. So let's start with the anisotropic flow that is measured in experiments, and I will start with this old picture that we have, that we know is perfect spheres. So the idea was that the whole thing could be modeled as a perfect spheres, Lorentz contracted, but real perfect spheres. They collide, and when they collide, they produce this almond-shaped geometry in the overlap zone, which is a perfect almond. So it has reflection symmetry about x and y. Okay, and that essentially, if I were to do a Fourier decomposition in the azimuthal plane for the spectrum, okay, then because there is reflection symmetry about x and y, the sine terms and the odd, the sine terms vanishes, as well as the odd terms of cos goes to 0. Okay. And this, this is it for the final state. So what I'm doing is that the fact the initial state geometry is smooth, also because hydro is not a stochastic equation, it's a simple deterministic equation. So the smooth profile will go to a smooth final profile as well, deformed in a different direction, but still smooth, which will carry the symmetries of the initial profile, which is the reflection symmetry. Okay. So then, so the old picture where, this smooth picture for flow is, they had this, we had this Pn, which are only even ones were considered. Okay. However, the recent picture, well, not so recent now anymore, by Alvar and Roland in 2010, 14 years, yeah. So what they said is that the real collisions have fluctuating nucleons inside the nucleus, and that leads to generation of all other harmonics that we missed. So for example, now that the symmetry about, reflection symmetry about x and y is broken, so we will also have sine term. Okay. So and also the odd terms in cos. So we can combine these two using these trigonometric relations to write it in this form in terms of cos only, but it will give this angle psi n, which we call, so essentially this should be the reaction plane angle. Okay. Or the participant plane essentially. But the point is, this reaction plane, this is not measured experimentally. So there are these planes that I will discuss now. So there is this reaction plane, there is this participant plane, x prime, z prime. So because of the fact that the collision geometry is kind of random, in the sense that the number of nucleons in the overlap geometry may not exactly coincide with the almond shape which we have in mind for the spherical nucleus colliding. Okay. So for example, this thick black dotted line, it gives the elliptic anisotropy for the overlap zone, whose symmetry direction, whose symmetry planes are defined by x prime and y prime. They do not coincide with x and y. Okay. So this angle between x and x prime is what I would ideally consider psi n to be. But these are, this cannot be measured in experiments. I cannot just measure the difference between this is the angle between x and x prime experimentally directly. But there is a estimate for that, which is called the event plane. Okay, angle. And so there is this reaction plane which is defined by x and z. Participant plane is x prime and z prime. Z may also have shifted because of the tilt of the fireball. Okay, so the point is, x prime and z prime, this plane is not the same as the xz plane. Okay, and these are not measured experimentally. What is measured is event plane, and that is what, and in the event plane we take this angle to be, proxy for psi n. Okay, so for simplicity, one can introduce this single complex variable, which is, so what I can do is I can take this form, okay, and rewrite it. I can introduce this complex variable Vn, which has this event plane angle. Okay, and with these definitions, you can one can just express it in terms of, this exponential. This is another basis for Fourier transform, Fourier decomposition of transform. Okay, so then the flow coefficients one can extract by simply taking the inverting this, which is the Fourier coefficients. Okay, and one can also extract the event plane angle psi n. Okay, one has to keep in mind that this whatever psi n we calculate, it has to be modulo 2 pi by n, because maybe because you are actually looking for this angle. How is it measured experimentally? So theoretically, we can have a very nice picture, but experimentally, this orientation of the reaction plane and participant plane, these are not known. Okay. Also, Vn is usually measured experimentally from even angle. So this azimuthal correlation of outgoing particles, that to event averaged. Okay. So this is how it's measured. So the idea is that what we have is in terms of moments. You can express it in terms of correlations and cumulants, and cumulant definition is more convenient. Okay, but this whole explanation on how it is measured and what are the correlations, it requires another lecture. It's a topic for another lecture. So I suggest maybe the organizers can consider this. And similarly, what we can do is we can characterize the initial state. This was the final state we had. The initial state is characterized in a more modern picture in this way, where the energy density obtained from, let's say, initial condition model like Glauber model is kind of decomposed, or rather written in so the nth component of the eccentricities can be obtained from the energy density distribution in the transverse plane. Okay, and this phi n is the angle in the participant plane. Okay, so psi n is the event plane angle, phi n is the participant plane angle, and we can of course again invert this and obtain whatever epsilon n and phi n in terms of this expectation values, which is defined in term here. Okay, remember this minus sign is put to keep epsilon 2 positive. We want that the epsilon 2 which I defined in those pictures were actually negative, but this is a convention essentially. Okay, we want the eccentricities to be positive, because as you can see the picture of the initial shape is elongated along y, but the final momentum anisotropy is along x. So one of them has to have the opposite sign. So you consider both of them positive and put a sign by hand as a convention, or one becomes negative compared to the other. Right, and it agrees with the old definition of second eccentricity. Okay, so yeah, more or less this is what I had to say about relativistic hydrodynamics and collective flow. So what I discussed is this physical intuition of these hydrodynamic conserved currents, and what does this conservation imply, and the form that these currents take in equilibrium, and how to include dissipation and the role of viscosity in flow. And in this collectivity and flow picture, we should look at the old and the new picture, and how to characterize the initial and final state. There are these references I would suggest for phenology of heavy ion collisions. There is a book by Larkowski. I would shamelessly push my own review article for basic framework on relativistic hydrodynamics, and a very nice review of flow can be looked into this review article by Rajiv Bhadarao sir. So it's very nicely written with exercises as well. So I would suggest students to work out those. And if you want to read on more advanced materials on relativistic hydrodynamics, there are these two. One is a review, and the other is a book by Paul Romatzke. I would suggest looking at that. I will end it with a quote from Michael Atiyah, which I copied from Bhadarao sir's review article. The aim of theory really is, to a great extent, that of systematically organizing past experience in such a way that the next generation, our students and their students, and so on, will be able to absorb the essential aspects in as painless a way as possible. And this is the only way in which you can go on cumulatively building up any kind of scientific activity without eventually coming to a dead end. So I hope I managed to convey this in a painless way. Thank you.
Thank you, Amaresh. Now we can have some discussion or question answers,
Yes.
though we had some in between to talk.
Hello, myself Dipendra.
Yes.
I have a question. In initial slides, you imposed the conservation law like particle conservation and energy
Right.
momentum conservation.
Mm-hmm.
So we impose this relation here to get this covariant form of the equation.
Right.
But in reality, we don't have the particle conservation. So
But
in
net
relativistic
particle would be conserved. In for example, relativistic case, even though particle is not conserved, okay, there will be some conserved, charge, for example, baryon charge or strangeness. So so total part, so by particle is just, when I say particle, I just mean, some conserved charge associated with the particle.
Okay,
So let's
okay.
say, electric charge, baryon charge, strangeness. And that too it's not the total strangeness which is conserved, it's the net strangeness which is conserved, net baryon number which is conserved. So we do have that.
Okay, I got it. Yeah, and another doubt is that we are considering the calculating the azimuthal. So we took the Fourier transform to get the
Right.
V2, where phi angle is important for seeing the V2. But in experiment, in each event, we can have different phi. So here,
You mean
so
psi n?
phi can also have different, right, in each event.
Phi is different, of course, yeah, but
So yeah, so in that case, how can we?
no, these Vn coefficients, they don't depend on phi. So indeed, this is phi p is different, okay, but phi p psi n will be different in each event, as you said. But this coefficient, Vn coefficient, that is what tells me the the anisotropy of the momentum anisotropy, that is independent of phi. Okay, that is what exactly we decompose into. So the phi dependence of the distribution here, for example. So as you can see, this dy d2 pt, d2 pt will have pt dpt d phi p. Okay, but d phi p is what? So this phi p dependence is what I Fourier decomposed. So everything.
Actually, I want to say that in each event there will be different firewalls. So one, suppose in first
Yes.
event the
Yes.
fireball is expanding more rapidly along x-axis,
Right.
and in the second event the fireball is more expanding faster along y-axis. So both fireball has different nature. So in that case, the phi would be how means.
Okay, so usually the way it is done is in the experiments they consider this
Amresh,
centrality
Amresh,
class.
I
Yes,
think this phi p is the particle phi, right?
yes, this
Yeah.
is particle phi p.
Yeah, so I
p.
think this is not the way the fireball is. This is the azimuthal angle of the emitted
Okay.
particles. And what we do in experiments, this Vn, as you correctly tell, this Vn is nothing but average of cos of n phi from this distribution. Right? Vn's are nothing but average of cos of n phi, or n of phi minus phi p minus psi n. So this average we take
Yeah.
first for all particles in an event, and then what I can do, an average over many events.
Right.
But this phi is a particle phi.
Now this is particle phi.
So they're indeed coming out in all directions.
Yes.
So the reference frame to measure this phi does not change in each event, right? It is fixed for each event.
Reference
So
frame
it is, Dipendra, it is taken care by the event plane angle. Na? Every event is different.
Okay.
Right.
Yeah, I
And
got it.
that too, for each harmonics, you have a different angle.
Yes,
Yeah. Even in one event.
That's why he has done, as Sadhana is telling, phi minus psi, na? So you
Yeah.
measure psi is basically different. What by
Psi is different for every
Right.
event. That's
phi,
what you're
by fireball, I think means the overlap zone. It has a tilt. So
Right.
that's why he does phi minus psi n.
Okay,
So
I got it.
whatever be the tilt, he is taken care of, and so that you can get all in the same reference frame.
Right.
Thank you. Yeah.
Hello.
Yes.
Could you explain the boundary term appearance in the energy momentum conservation tensor?
Okay. Here, this one, for example. So
Yes.
this is we are
previous
integrating over the 3d3x, 3 volume. So this term is like del xi
Yes.
of a quantity. Okay. Now this is just current, this particle current. NIx is a particle current, yeah. So what
Okay.
this means is that the current has to vanish at the boundary. If the current doesn't vanish at the boundary, then the medium extends beyond that. Okay.
Could you explain that again?
So what you can do is you can take this. This is the volume integral. Okay, you take this term with the volume integral, and using Gauss law, you can put it as a surface integral.
Okay.
Okay, and the Gauss law tells you that then this becomes just, because there is d3x and del x, so it is just ni at the surface.
Okay.
Okay, And Ni at the surface has to go to 0 because, this, otherwise if it is not 0 there, then there will be flow out beyond the whatever system you are considering. Yes, define a system boundary. So system is confined within that boundary. So at the boundary, all the physical term properties has to go to 0. That's what it means.
Okay,
Amaresh?
this is for the current.
This is the current.
And another similar thing was there for T. Yeah.
Yes. Similarly, here you have this momentum flow. Okay.
Okay.
Momentum flow. So
No, the question is in the first right side, left side, there is in the same slide.
mhm. Okay.
Okay. So here I have in
This is the boundary term.
the left side I have this integral, which gets me to this middle integral, which has the first term as same as previous integral.
And basically I've
And
added
we
a
are
0. And basically I've added a 0. That this is 0, nothing else.
why is it 0?
Yes.
Because it's the surface term again. Derivative of whatever this Ti nu x with respect to xi. So it has to go to 0 on the surface. So basically when I take this term and integrate over the volume, I can again do a Gauss, Gauss law. I can use the Gauss law
Okay.
and put it as surface. This will become Ti nu on the surface, which is essentially 0. So I just have added a 0, similar to here.
Okay.
I just have added a
okay.
0. Okay.
All right. All right. Thank you.
Amresh, can I just ask one point?
Yes,
I am
yes.
also having confusion here. So
Right.
you have this total derivative ddt of nt equal to 0, but
Right.
ddt can't be write directly as del t plus grad dot. So
One can
this,
do that, but
so then this
this
equation
n
directly will
n
give
is
you
a
the
total.
middle term of
This n is
Yeah.
not this n actually. What I am trying to say is this n is integrated over the density. So
right.
this is just the total number. The total number is just a function of time, because what I did was I integrated over the spatial x. Okay. So this x as t and x, so I integrated over the d3x. So it's just a function of time.
Right.
But the conservation tells me that it cannot be a function of time. It cannot change. The total number has to be conserved if it's a conserved quantity. Okay.
Right. So can't I just put this del t inside the integral, and then this ddt can't I write a del t plus del xi?
Del t is so ddt. Okay, because what I did was I operated ddt on both sides. Okay.
Right.
So ddt is essentially here x is a function. This is both t and x, function of t and x. So this
Right.
ddt just becomes a partial derivative for n0, because n0 is a function of two variables.
Okay.
Okay. And then but x and t are independent variables. So it is not like I will get a del x by del t is not allowed.
Okay. Okay.
Okay, that's why we don't have that term. I think that's what you are mentioning.
Yeah.
These are independent coordinates.
Can I ask one question?
Yes, yes.
So we have
Yeah.
hand from Neil Kamal. I think so he's raising from a long time.
Yeah.
So we'll take Neil Kamal's question and then we'll take yours.
Thank you, Sadhana. Hello, Amresh sir. So this
Yes,
is a very
hello.
formal and nice introduction to the subject. Thank you for that. So I have two questions basically. So the first question is, from recent Bayesian analysis, it has been concluded that eta by s and zeta by s both depends on temperature. Now,
Yes.
what they do is they fit an empirical kind of formula written as a function of temperature for eta by s and zeta by s. So my question is, do we have, like, from hydrodynamical calculations, do we have such formalism where we can actually get this temperature dependence of eta by s and zeta by s?
Okay, so as I said, within here, when I was describing this, I said that these quantities, these dissipative quantities, depend on two factors. One is the gradient, and the other is the material property. The material property, eta, zeta, and kappa. Okay, these are the properties of the QGP, the inherent property of QGP, for example, or water, if you are considering water. Okay, so for that, I have to really go into calculations of how the molecules of QGP or water behave or interact with what cross section. Okay, to calculate eta and zeta. So these are done, for instance, in you can do it with some kinetic theory calculations, assuming some scattering as a elastic scattering, or even I think eta zeta is also estimated in lattice. Okay, so you can,
Okay.
but not in this hydro.
Some people have calculated using this Kubo formula from thermal field theory also.
Thermal field theory, ADS CFT. Okay, all this has been, yeah. So there are these results, but what I'm saying is that within this framework of thermodynamics and hydrodynamics itself, you cannot obtain this eta and zeta and kappa,
Okay,
because
yeah.
these actually require to have more information about how the ingredients of the medium behave, how they interact. Okay, so
So that being said, the current models like EcoQGP, music, they do not have such formalism in it.
no, what they do is they will, for example, in hydro, even the equation of state would, if I want to specify it, I have to, let's say, go to kinetic theory within or I have to use lattice QCD. It's an external input being given to hydrodynamic equations to solve it. So I can also give an external input for eta, zeta, and kappa, as a parameterized form.
Okay.
That's what the fit is. That's what this Bayesian fit is. You give a parameterized form, and the Bayesian fit does what it does. It tells you how the parameters, what values it can take, or correlation between the parameters what to get from Bayesian.
Subject to the data.
Yes.
Okay, thank you. So the second question is very naive. So we observed that for different particle species, we have different flow. For example, in low PT, where the hydrodynamics works really well, we typically observe a mass ordering. So how that mass ordering picture is coming into picture, from the hydrodynamic itself, because how the mass is going into the play.
Okay, so this is very nice. Actually, this has I have to go into the freeze out prescription that I did not. So the mass ordering.
Because from experimental point of
Yes,
view,
I know.
we usually write that it is from radial flow and increased kinetic energy. But from hydrodynamic point of view, how the mass of different species play a role there.
So let me just give you a nice picture. So here, for example, this hydrodynamic expansion that I am showing here. Okay. So when the medium is expanding hydrodynamically, okay, there is no particle picture at that point of time. It's a continuous medium which is expanding hydrodynamically. Okay. And then at some point, so basically the fluid has gained some momentum along, there is an overall momentum to fluid particles, which is going along X or Y. Okay. Okay. Now what you do is at a given point you go to the fluid cell and you produce particles. So that at a given momentum you produce particles. So at a fixed momentum in a fluid cell, if you produce particle which is heavier, it will be moving slower.
Okay. So this is happening at the boundary where you are converting fluid cells to particularization models, using particularization models.
But I don't know whether this really answers the question very correctly.
Yeah, if I can comment on this.
Yes.
So I think in Israelist world, like bulk viscosity or shear viscosity, they have introduced this mass term. So they have very old paper, like 1998 or something, or older than that. So there they have put one way to include the mass terms in the dissipation part. So,
No, that he's not talking about dissipation. This it even occurs at ideal level. Mass ordering, you can see even at this is
ideal. Then I think it should be massless in that case.
No, ideal does not imply massless. No, that's not true.
Okay.
Ideal does not imply massless. Yeah, that is a conformal thing. So this confusion I usually try to clear for people that epsilon equal to 3p is not ideal. Epsilon equal to 3p is ideal, of course. I mean, this is the equation of state it holds in equilibrium. Okay, but then ideal is just when there is no dissipation. I mean, epsilon equal to 3p is conformal. It's a more specific picture. It's a massless case.
Yeah, massless case.
Yeah, that is not.
Because it is defined for basically photon gas. So considering photon gas massless.
But okay, coming back to Neil Kamal's question, I think okay, maybe that nice picture that I tried to put forward, maybe that has some intuition, but I'm not sure if that is. Maybe I'll send you some reference, Neil Kamal. Okay.
Okay, sir.
I think it requires the freeze out prescription, and that I did not discuss here. So
yeah, okay. I think So basically from the U mu P mu term,
Yeah.
so that comes from that one only. So
Mm.
there the mass is there.
Yeah.
So
the
that
particle
ordering
mass
will
is
come
there.
from that.
That mass ordering comes from freeze out. Yeah, yeah.
Yeah.
Mm.
Okay,
Yes.
nice. Okay, thank you.
Yeah, so I have very small, not questions, kind of discussion. So, like baryon number conservation is mandatory to solve these hydrodynamic equations. But like going, if you consider a Beeson scenario where this baryon number conservation is not there, then how could we solve this hydrodynamic equation for such a system? Like we know that energy momentum conservation is there, but
Mm.
other conservation is not there. Then is there any way to solve this thing? Or you were just thinking?
I mean, no. If there is no baryon number conservation, then you don't have a chemical potential, for example, which corresponds to a. So each conserved quantity would have in the statistical mechanics picture, it will have a Lagrange multiplier, which corresponds to this conserved quantity. For example, for energy momentum tensor, the Lagrange multiplier is this beta mu, which is beta times u mu. Okay. For baryon number conservation, there will be alpha, which is mu by t, and so on.
Yes.
So if you don't have this, then you don't have the alpha. I mean, then there's one variable less anyway. If you don't have an equation to solve, you don't have a variable to solve for. So then the set of equations should be closed. So there is no issue. I mean, even if you don't have a conserved current, so what? I mean, whatever the variables you have, number of equations should be the same, if everything is correct, of course, provided that you have equation of state as well. Yeah.
Okay. Thank you.
Okay.
Hello, sir.
Yes.
Sir, slide number 16. The kappa is thermal connectivity or charge connectivity you mentioned.
Here it's charge
16th slide.
connectivity. Here it's charge
Charge.
connectivity. Yeah.
There is a hand raised from Rishabh.
Yes, please.
Yeah, thank you. So I wanted to understand how does this collision centrality affect the higher order eccentricities that I think you spoke about towards the end of your talk?
Yeah, well, I mean, these here, I think.
I think next.
Yeah.
Yeah, this one.
Right. So, of course, to get this energy density from a Glauber model, the Glauber model requires you to give an impact parameter. So that theoretically, it's a very well-defined thing, right? If I want to have an energy density distribution in the transverse plane, I can give the input to the Glauber model as which nucleus I'm considering and what is the impact parameter. Okay. And then the Glauber model simply takes this inelastic sigma collision cross section you provide, and then it will give you the energy density distribution. But impact parameter is a theoretical concept. What do you have as a proxy to that experimentally? And that is centrality, collision centrality. Okay.
Right.
So this,
Yeah, the question what I wanted to get at was basically how do I picture it intuitively? Like I understand that you have this energy density and based on that you get these eccentricities. But for example, let's take the second order eccentricity, right? We know that higher the centrality of the collision, less elliptical the interaction area would be, right?
Right.
How do I picture that, let's say in case of epsilon 3 or epsilon 4?
Okay.
Yeah.
So this is the idea is that except as in my naive understanding of this whole picture, the only eccentricity which is due to geometry is epsilon 2. Everything else I consider fluctuation. Okay. So if it is geometry, I would so epsilon 2 is the one which controls the geometry of the collision. Okay. Then and that's what I measure in when I when I try to estimate centrality. Everything else, all higher order harmonics, they are fluctuation, and I don't have any picture for that, intuitive picture for that on how to connect it to centrality. That I don't know if Parthuda or someone else will like to comment on that. I am limited by my knowledge here.
Okay. Yeah, anyway, thank you.
Okay.
Yeah.
I think Arun has a question to ask.
Yes, Arun.
Sir. Sir, my question is regarding this plot of V2 versus PT.
Okay.
Sir, here we see that ideally the expectation is that the V2 should just increase as a function of PT, and even for small eta by S. And
Okay.
experimentally, we have seen that it increases and then decreases around 5, it decreases because of viscous effects. The question is that is there a physical like expectation or explanation why this, at least for low PT, why this increasing behavior should be there as a function of PT? Or it is just an observation that we have, or is there a physical explanation that why this nature is there?
Okay, it is more like how the viscous corrections, okay, how it plays a role. So for example, you would like to, when you produce particles or when you calculate V2, you would like to have a correction to the distribution function here. This is equilibrium. So if you would like to have a correction to the distribution function, which is viscous in nature and dissipative correction, okay. This dissipative correction, there are many forms. So of course, the form of the distribution dissipative correction would very severely restrict this calculation for V2. Okay. So if the point being that if this delta F is whether it increases linearly with momentum or quadratically with momentum, okay, there are these two forms that I know of. Okay, that would play a role on how fast it is suppressed at higher PT. Do you get it?
Yes, sir. But the question is, even for say low PT, see for all kinds of viscosity and even for ideal, for low PT we have an increasing trend. I wanted to know if like there is a physical explanation to that. Like why should it be an increasing? V2
low
should
PT
increase.
comes from this calculation. Low PT comes from this. I mean, from the equilibrium. You want a intuitive picture. Why it
asking Amaresh, like when you say the spectra, in spectra we always see a falling nature, right? From equilibrium, you see that higher beta is smaller beta yield. But in the V2, we just see the opposite, right? At higher PT, it is an increasing nature. Forget about viscosity. Just for ideal hydro, this is an increasing nature. So why a priori one should expect, or can we understand this increasing nature from the hydrodynamic considerations?
Okay, so the spectra is very easy to understand. We see the decreasing nature in the log linear plot because it just goes as the thermal distribution, exponential of minus. It just slope of the thermal distribution, roughly. Okay, that is for spectra. But this one is a ratio, this quantity. Okay, now as a function of PT, okay, so high PT behavior is completely controlled by delta F. That is for sure. At low PT, so
you are taking an average over cos 2 pi and your weight function is your spectra.
Right. Yes, but why is this Vn, which is a function of PT, not phi, PT and y? Why that is increasing as a function of PT? Okay, I will think about it. I don't have the answer to that. I mean, intuitive answer. I know how to calculate it, and okay, but think about it.
Okay.
Any other questions?
I think probably there are no more questions. Sadhanati, you are there?
Yes.
Okay, so you then take over, please.
Maybe just last one, just Amaresh, just a comment. So if you take, for example, the flow of the energy instead of the flow of the particles in the Landau framework, so at the observable level, what kind of changes or you expect?
Your voice broke out. Can you repeat again? So if I take Landau frame.
Yeah, Landau. So basically energy flow instead of particle flow. So at the observable level, whatever we are observing,
Mhm.
So, is there any change or there is no change at all?
So
Any kind of
frames are,
observable, maybe rapid stress. Yeah.
yeah, so frames are physical constructs, so it cannot affect observables. It should not affect observables. Okay. So whether we work in Landau frame or Eckhart frame or any other frame for that matter, should not be affecting any observable, should not have any observable consequences.
Okay. Only we will choose the frame according to our situation.
Which is our according to our convenience. Yeah.
Yeah. Okay.